and welcome to week 2 of AP Calculus. What we're going to be talking about today is to determine limits at infinity and horizontal asymptotes. Make sure that you have checked the weekly calendar, you've got it all up to date, and you know what's going to be expected of you this week. So you're going to be doing homework from Chapter 2, Section 6. So if you've got everything ready to take notes, let's get started. So we're going to be talking about limits at infinity and then their horizontal asymptotes. So as a reminder, limits at infinity are when you see a limit as x approaches positive or negative infinity like this, and it's what happens as x increases or decreases without bound. Another way to think about this is a function's behavior at the ends of the x-axis, so all the way towards the negative or all the way towards the positive. For most of these, this will be where it either goes towards infinity or doesn't, but in some cases you're going to have a horizontal asymptote, which means as it goes towards infinity, it will flatten out in some way. So a horizontal asymptote occurs if the limit as x approaches positive or negative infinity of a function is equal to a number rather than equaling positive or negative infinity. And there aren't a ton of functions that have horizontal asymptotes, but you're going to see a lot of them today because that's, the functions that we're interested in at infinity. One of the ones that students tend to forget about a lot but show up in many calculus problems are tan inverse. So we're going to find the limit as x approaches infinity of tan inverse of x and as x approaches negative infinity. So some of you asked about this last week and saying, okay, well, is looking at a graph a exact enough way to find out some of these limit answers? And absolutely it is. So if you want to plug it into your calculator, or if you remember what the graph of tangent of x looks like, it looks basically like a tangent graph turned on its side. It goes to the origin, just like this. And it will look like that, and it does have two horizontal asymptotes, just as tangent has vertical asymptotes around this same point at the origin. And the idea here is these occur at the same place that the vertical tangents would occur for the graph tangent, which is at positive pi over 2 and negative pi over 2. So in this case, as it approaches positive infinity, here we're at the positive 1. So limit as x approaches positive infinity of tan inverse is pi over 2. And here it's negative pi over 2. And it's just nice to review these because they show up a lot when we talk about things approaching infinity. Another type that shows up a lot are these rational expressions. So you've learned a couple tricks to deal with these using division, multiplying by 1 over x to the third, things like that. But here's a nice trick that you can do. If you see polynomials and x approaches infinity, the behavior isn't going to be affected by these terms. Basically what I mean by that is if you have x is equal to 10 billion, adding 14 stops mattering after a while. As x gets huge, only the highest degree terms matter, so you can actually drop the rest, just so that there's 1 in the numerator and there's 1 in the denominator. So what this is basically saying is that the end behavior of the original polynomial is the same as the end behavior of the simplified, which is the only part of the thing we care about when x approaches infinity. And then we can just treat this like a much simpler problem. We can simplify the x terms away. We end up with the limit as x approaches infinity of 5x over 3, which means that it doesn't have a horizontal asymptote. This is just infinity, which is the same as d and e. I'm fine with you writing it in either way. Now, this is just a nice trick because it saves a lot of time. What we can see in number 3, we're going to drop those final terms the same way. Now we have the limit as x approaches infinity of 5x cubed over 3x cubed, which simplifies much easier. And so now it's the limit as x approaches infinity of 5/3. There's no x, so x doesn't even matter for this problem anymore. And we just end up with 5/3. Again, if you want to do the multiplying by 1 over x to the third trick, that absolutely works. This way is just a little bit faster. We'll have things approaching infinity when they aren't in fractions, where they might be a subtraction problem. Because when we plug in our answers here, if we would get an indeterminate form, if we plugged in infinity minus infinity squared, we now get infinity minus infinity, which is like, is that 0? Is that also infinity? Who's to say? So one way you can handle this is that it's easier to deal with infinity and things like that when we're talking about factoring. So if you're looking at a problem and you're not sure what to do, factor is always a good option, which in this case will become the limit as x approaches infinity of x times 1 minus x. Again, since we're only thinking about what's happening at the end, the 1 isn't going to make a huge difference. So then you have limit as x approaches infinity of x times negative x, which is the same as limit as x approaches infinity of negative x squared, which is negative infinity squared, which is negative infinity, or again, dne. All right. Hope this helped clarify some things, give you some new ideas. If you have any questions, leave them in the comments, or you can grab one of the appointment slots in the calendar. Those aren't mandatory this week, but are definitely going to be helpful if you're stuck on any of these problems. Leave your nominations in the form and make sure to turn in 22 into Google Classroom. Have a great day, and I'll talk to you later.